Hey everyone, we are back with another live stream. We're doing another live office hour brought to you by Chegg. I'm working with Chegg to bring you Organic Chemistry 1 office hours this entire semester every Tuesday at 5 p.m. PST. And so we've got just a few more of these. I know that most of you guys are wrapping up your semesters very soon. And so there's going to be a few more. I just wanted to let you know that next week, the Organic Chemistry 1 session with me is going to be exclusively on the Chegg website. So it will not be live streamed on my channel or any other channel. It will be exclusively on the Chegg website, and you will have to log into the website in order to view it. So if you've been enjoying these study sessions and would like to study with me next week, go ahead and go to the Chegg website and log in for that. And also check out the QR code on the top left if you want to see what other subjects Chegg is covering. They're doing all kinds of different topics with different instructors. And so definitely coming into final season here, you need all the help you can get. So I'm helping you with Organic Chemistry 1, as always. And we are live in the chat. And so I'm taking any questions you have. Please keep them Organic Chemistry 1 related. They can be related to the questions that I prepared and will be going over for you. They can also be unrelated to these questions. You can ask me any question about any Organic Chemistry 1 concept, and I will be scanning the questions and doing my best to answer all the questions that you have. So let's go ahead and get started. I have a bunch of different things here. So we're reaching final season, so I want to do some review. I want to try to mix it up, do as many topics as possible. So let's start with this first one here. Draw the product of the following transformation. And so we have this hydrocarbon, we have an alkane, and then we have bromine, and then HV. Light. This is light, and then wavelength. And so what we're saying is that this is radical bromination. And when we do radical bromination, what do we end up doing? What ends up happening is we're placing a halogen, we're placing, in this case, a bromo group on the alkane, and then we want to know where it's going to go, right? What do we have to say about regioselectivity? So it turns out that chlorine radicals are not particularly regioselective, but bromine radicals are. And so when we're talking about radicals, what we mean here is that the bromine-bromine bond is pretty low energy, and so it can have a tendency to homolyze rather easily. And so that's what the light is for. If this bond is struck with a photon of a particular wavelength of UV light, it is going to homolyze, and we get our bromine radicals. Now, without going and doing the whole mechanism here, because last week, I believe it was, we did the radical chlorination mechanism. This is absolutely identical, just with bromine instead of chlorine. So the bromine radical is going to interact with a particular carbon-hydrogen bond. And in doing so, it will grab a hydrogen radical to become HBr, and it will leave an alkyl radical. But what kind of radical will it leave? It could leave a primary radical, it could leave a secondary radical, or a tertiary radical, depending on which CH bond it interacts with. And as it happens, because the bromine radical is much more stable compared with the chlorine radical, it's going to be much more regioselective and go via the pathway that yields the most stable alkyl radical intermediate. So what that means is that we're going to end up with this as an intermediate, right? We're going to have a radical either here or here. And so what that means is that there was an implied hydrogen right here on that tertiary carbon, but the bromine radical interacted with that, got a hydrogen radical, and left the tertiary alkyl radical, right? And so then this alkyl radical is going to interact with another equivalent of bromine, of diatomic bromine, and get the bromine on there. So this is what we're going to end up with. So now we don't have implied hydrogens anymore. So we have to, in fact, why don't we just go ahead and put this as a wedge too, right? This could be a wedge or a dash, doesn't matter, because we have two identical methyl groups. But we want to depict the sp3 nature over here. And the bromine also we can put on either the wedge or the dash because we have two identical methyl groups. So it doesn't matter if we were to rotate around that sigma bond. we would get the other conformation. It would be identical. So when you are doing radical halogenation, right, we can do this with, well, you can do it with fluorine, but it's very explosive. Chlorine and chlorination and radical chlorination and bromination are common, right? Radical fluorination is dangerous, so it's not done as much. Radical iodination is difficult to do because the iodine radical is not very reactive. It's quite stable. But radical chlorination and radical bromination are very common. And then we want to understand that if we were doing radical chlorination, where the chlorine ends up would be a toss-up, right? The chlorine radical is so reactive that it will react with the first carbon hydrogen bond that it collides with. Right? It's just going to collide with a random part of the molecule and then grab that hydrogen radical, and you'll get either a primary or a secondary or a tertiary alkyl radical. And then that will then go ahead and get a bromine radical and become the alkyl bromide, or sorry, alkyl chloride. But for bromine, it's much more regioselective because of the stability of the bromine radical, right? And that has to do with size, right? It's just that bromine has another shell. Bromine has one more shell than chlorine, right? And so it's similar with like how the bromide ion is more stable than the chloride ion, is more stable than the fluoride ion. It's about ionic radius. So here it's the same concept, right? It's just the radius of that radical. It's so much larger, and we're talking about a form of electron deficiency here. So it's going to be more stable. And so we proceed via the most stable alkyl radical intermediate. And so that's where the bromine ends up. So all of that is to say, right, hopefully all of that made sense. But if you just want the take home, if you just want the quick one sentence take home, if you have an alkane and you're doing radical bromination, all you do is you stick a bromine atom on the most substituted carbon. That's it. Right? So here, not primary, not secondary, tertiary. We've got two identical tertiary carbons because it's a symmetrical molecule. So all we're doing is we're taking a bromine atom and sticking it on the tertiary carbon. That's it. That's the whole reaction there. So that's a little bit about radical halogenation in general and radical bromination in particular. Let's see if I missed any questions. Lesson notes, Danny says, is it starting from next week? Everything will be done on the Chegg website. I believe it is only next week. So next week, May 6th, will be on the Chegg website. I believe the week after will be back to being live streamed on my channel. I can double check on that. And then he asks substitution reaction. So no, this is not a substitution reaction. This is actually radical halogenation. So it's a different class of reactions. And so Minecraft player asks, why does the bromine go on that one? And so, like I said, it has to do with the stability of the bromine radical over the chlorine radical. Because the bromine radical is so much more stable, this is going to be able to proceed by the lowest energy pathway, which means the lowest energy intermediate. The lowest energy intermediate is the most substituted alkyl radical intermediate, right? Alkyl radicals are more stable as they're more substituted, right? The methyl radical is very unstable, and then better is the primary alkyl radical, and then secondary, and then tertiary, right? And so if the tertiary alkyl radical is the most stable possible intermediate for this pathway, the bromine radical is going to promote that pathway. So it's going to wait until it collides with a tertiary carbon-hydrogen bond, get that hydrogen radical to become HBr, and then you're left with the tertiary alkyl radical intermediate. So the reason for the regioselectivity has to do with the stability of the bromine radical over the chlorine radical and the stability of the more substituted alkyl radical over the less substituted alkyl radical. So those are the two reasons in conjunction why that goes that way. What is halogenation? That's when you put a halogen on the molecule, right? Halogen being group 7, fluorine, chlorine, bromine, iodine, and astatine, which we do not really use much in chemistry. Minecraft player, is there a way to select one of the regions like temperature or pressure or something? So no, not really, right? We're talking about the relative stabilities of the intermediates. Yeah, that's really all there is. So Danny asked, why don't you add another bromine and the other carbon? So yes, you could. You could do successive brominations, right? Chlorination is hard to stop because chlorine radicals are so reactive. Bromination is slower because bromine radicals are more stable. So it is actually possible to isolate the monobrominated product. So you could do a monobromination and then isolate the product, but you're not wrong, right? If you let this go for a long time, you will get the dibromination product. You would get another bromine right here, right? If we just let this sit around for long enough, you're going to get another bromine radical interacting with the other tertiary carbon bromine bond. But usually on an exam, if you're looking at radical bromination, you're probably just being asked about the monobromination product. Oh, JA asks for Michael addition. Okay, yeah, I can probably throw in some Michael addition at some point. Let me see where I end up having room for it. Okay. Okay, moving on to the next one. I'll put Michael addition in the back of my head, see where I can fit that in. Okay, so draw the product here. So we have a secondary alcohol, and we're reacting with tosyl chloride in pyridine. So what is tosyl chloride? Tosyl chloride looks like this. So here's tosyl chloride. This is a tosyl group, and then this is the chloride. And so what we need to understand is that this will interact with a hydroxyl group to make it a good leaving group. And here's why that is the case. So the oxygen, a lone pair on oxygen, is going to attack the sulfur, kick this pi bond up here, and then let's just save some time. We're going to bring that back, and then we're going to kick off the chlorine. And so what we end up with is we have retention of stereochemistry, and then that is now O-tosyl. So this can be written like this. I'm going to write it like this. I'm just writing it like this to help explain what's going on. But if you were, what you would probably do is just this, right? It's tosyl chloride. So tosyl, so tosyl is this. That's a tosyl group. Okay. So it's tosyl chloride, tosyl, and then chloride. So it's a tosyl chloride. And this is a way of making a leaving group derivative. So the purpose of this is that the hydroxyl group is a bad leaving group, right? Unless you're in extremely basic conditions, you're not going to get a hydroxyl group to leave, because if it leaves, you have a hydroxide ion. A hydroxide ion is very reactive. It's very unstable. And so things, right, the leaving group ability depends on how stable something is once it leaves. So a water molecule, right, OH2 plus, is a very good leaving group because once it leaves, it's a neutral water molecule. A bromo group is a great leaving group because the bromide ion is very stable, right? So, but the hydroxyl group is a bad leaving group because once it leaves, it's hydroxide. That's unstable. But if we have it react with tosyl chloride, if we tosylate it, right? This is a tosylation because we're putting a tosyl group on there. Now look what happens, right? We can do this. Let's react with KCN. So potassium is just the counter ion. CN minus is the nucleophile. Now this can do SN2. So whereas an alcohol could not be an SN2 substrate, this can be. And I'll show you why. So we get our SN2 product. And remember, with SN2, we have inversion of stereochemistry. So the O-tosyl was on the dash, so CN is on the wedge now. And then what we also have is we have this. And the reason this is now a good leaving group is look at all this resonance, right? We've got resonance over here. We've got resonance over here. We've got resonance all over the place. And so resonance, the fact that there's all this resonance stabilizes that negative charge, right? We have a lot of resonance stabilization. So this O-tosyl is a good leaving group because of all this resonance stabilization that's not there for hydroxyl, right? The hydroxyl, if it leaves its hydroxide, right? OH minus, there's no stabilization, right? This negative charge is localized on that oxygen atom. It has nowhere to go. But O-tosyl, there's tons of resonance stabilization. This is perfectly fine. This is an excellent leaving group because it's so resonance stabilized when it leaves, right? So this is a leaving group derivative, right? When you see tosylation, we're talking about generating a leaving group derivative. We're talking about turning a hydroxyl group into a good leaving group for an SN2 reaction or something else, maybe for an elimination. I don't know. But the point is that hydroxyl won't leave, but if you tosylate it, it will. So we also could have done an elimination. CN minus happens to be a classic SN2 nucleophile. So we knew we were going to do SN2. But let's say we got some tert butoxide on there, then we'd be doing E2, elimination, right? Because this would be, right, a leaving group is a good leaving group, whether it's substitution or elimination. It's got to leave whether you're replacing it, substituting it with another group, or forming the pi bond and kicking it off when the pi bond forms. Doesn't matter. Leaving group has to leave. And O-tosyl is a good leaving group where hydroxyl is not. Okay, so tosylation, where it's so we tosylated this oxygen attacked the sulfur. We got the tosyl group on the oxygen. Now it's a leaving group derivative. It's a good leaving group. So the SN2 nucleophile attacked, kicked that off. We got an inversion of stereochemistry, and there is our SN2 product. So we did SN2 on an alcohol. Right, we did SN2 on an alcohol, which you wouldn't be able to do. You have to do this leaving group derivative method here. Okay. What is tennessine? Oh, no. TS is tosyl. Tennessine is TN, I believe. Yeah, TN. Colorado asks, how do you know what is stable and what isn't as far as leaving groups go? So the leaving group ability is proportional to the stability of the group once it has left. So if it leaves, how stable is it once it has left? Hydroxyl is not stable. It's got a formal negative charge that is localized entirely on one atom, right? O-tosyl is a great leaving group because that negative charge is resonance stabilized. So the more stable the leaving group is once it's left, the better leaving group it is, right? Placating content. This is just typical OChem 1 content, but that's all it is. Aldol condensation mechanism. Okay, so we're being we want to do aldol and Michael. Those go together. So maybe I'll just do that next. Berlioz asks, what happened to potassium? Was it used? So no, potassium. So it's just, we have to get really good at recognizing ionic compounds, right? Because we're going to be given KCN, but the potassium is just the counter ion to our SN2 nucleophile. It's just a spectator ion, right? We say KCN because that's what it is. When we go to the stockroom, right, we can't store CN minus ions. Right, ions form ionic compounds with counter ions. So the cation, the potassium cation, is the counter ion to the CN minus nucleophile that we want. But so we say KCN because that's what it is. We go to the stockroom and we get the KCN pellets, right, and then we weigh how much we need, and then we put them in there. But the potassium ions don't do anything in solution, right? I mean, at best they complex with the with the oxyanion on the leaving group, right? That they may have an interaction there, but in terms of mechanistically, they're not doing anything important. But they're there, right? But so I do find that this is a confusion for a lot of students. Make sure that we know the difference between KOH and ROH, right? KOH is ionic, ROH is covalent, right? So this is strong and this is weak, right? Because potassium hydroxide, we have a negatively charged hydroxide ion. With an alcohol, it's totally covalent, right? There's no negative charge there. So it's a much weaker nucleophile or base. So yeah, let's make sure we can recognize counterions when we see them. Okay. So I had a question about, or somebody wanted to go over aldol condensation and Michael addition. So let's do that. So let's say we have propanol and benzaldehyde. So, and then we have strong base. Okay. So what we need to understand is that when we have a very strong base in solution with ketones and aldehydes, we have the potential to be doing enolate chemistry. There's a bunch of different kinds of enolate chemistry: aldol condensation, Michael addition, Robinson annulation. Not right now, buddy. Robinson annulation, Claisen condensation. We got a bunch of stuff, but they all proceed via enolization. We're going to form an enolate. So we have to understand that protons that are alpha to a carbonyl are mildly acidic. So this is around pKa 19. And it is because it is alpha to the carbonyl, right? Carbonyl carbon, alpha means 1 over. So here's the alpha carbon, right? That's the alpha carbon. So let's take the hydroxide and let's get that proton and let's go right here. And then let's kick that up there. We've got our enolate now. So here's our 3-carbon enolate. And so remember, right, we got this alpha proton, we made the pi bond there, kick that up there. Now, enolates are sources of nucleophilic carbon, and they attack other carbonyls, right? Because there's another, I'll just draw the other resonance structure here, right? The other resonance structure has a formal negative charge on the carbon, on the alpha carbon, right? And so you can use that one in the mechanisms if you want. I like to use the other one because it's more strongly contributing, right? The resonance structure with the oxyanion is more strongly contributing than the one with the carbanion because the oxygen can better accommodate the negative charge because it's more electronegative. But that doesn't mean the other resonance structure is contributing to the composite. So we have a situation where we have nucleophilic carbon. And so the nucleophilic carbon can attack a carbonyl, and we've got benzaldehyde over here. Now, I should make it clear that we enolized the propanol, not benzaldehyde, because benzaldehyde is not enolizable. There is no alpha proton. So this carbon right here does not have any implied hydrogens, right? This is a benzene ring. So we've got we have 4 bonds to other carbons, a single bond to one of them, a double bond to another, and then a 4th bond to the carbonyl carbon. So there's no implied hydrogen on this carbon here. And then the aldehyde carbon is not acidic, right? It's an alpha proton, not the aldehyde proton, right? So this proton over here, that one is not acidic either, right? It's alpha proton. So so that attacks there. And we get so we did this. We made this bond. This is the new carbon-carbon bond right here. Okay. And so a couple of things. Number one, we want to make sure when we are assembling the larger carbon skeleton, right? One fragment attacked another fragment. We don't want to gain or lose any carbon content, right? So we had a 3-carbon aldehyde, 1, 2, 3, and it was carbon 2 that did the attacking. 1, 2, 3. Carbon 2 was the nucleophilic carbon that attacked the carbonyl carbon, but we didn't, whatever other carbon material is there, it better still be there. We're not going to break any carbon-carbon bonds. So here's carbons 1, 2, 3. So this third carbon is tucked out of the way over there, but we can't lose it, right? This is a very, very frequent error that I see with students, is that they'll forget that third carbon. They'll just lose it. But make sure it's still there, right? So count. You can number your carbons if you need to. But then carbon 2 attacked the carbonyl carbon. So this was the carbonyl carbon. Carbon 2 attacked, and so there's our new carbon-carbon bond. We have a larger carbon skeleton now. And then let's just get, we'll grab a proton from water. This is all aqueous here. And we're in strongly basic conditions, so we can produce another hydroxyl. That's fine. We'll do that, and get the hydroxyl there. And then we can do base again. And if we heat it up a little bit, especially, it's going to go this way. So we'll raise the temp a little bit. And the reason we're doing this is we have another alpha proton there, right? There were 2 alpha protons here. There were 2 implied hydrogens over here. We got one of them, but there's one left. And so let's take this and get that last proton, last alpha proton, and then we'll go here, and then we'll kick off the hydroxyl, because again, in strongly basic conditions, hydroxyl is a legitimate leaving group. That does work. And so that gives us our aldol condensation product. So this is the aldol addition product right here, where we have a beta, it's a beta hydroxyaldehyde. So we have the carbonyl, and then in the alpha beta position, right? So here's the alpha position, here's the beta position. We have a hydroxyl on the beta position. That's the aldol addition product. But the aldol condensation meaning we lose a water molecule, and by a water molecule, I mean a proton plus a hydroxide. H plus OH minus altogether is a water molecule, right? The hydroxide grabs a proton, it'll produce a water. Right. And so the product of an aldol condensation is we have a degree of alpha beta unsaturation here. Right. Here's the alpha carbon, here's the beta carbon, and here's a pi bond between the alpha and beta carbons relative to the carbonyl. So this is what an aldol condensation product looks like. Whatever carbonyl was involved in enolization, that carbonyl reforms. So that carbonyl better be in the product. And then we have a pi bond between the carbons that are alpha and beta with respect to the carbonyl carbon. Okay. So if you're doing aldol condensation, there better be a carbonyl in it, because we're reforming the carbonyl that was part of the enolate. And then there has to be an alpha beta degree of unsaturation. Okay. So that's that. Yeah, that's like a standard aldol condensation. Let me see if I missed any questions. Oh, yeah, Tommy has asked a pretty good question. So, why does the alpha carbon act as the nucleophile? So, the thing is, you would be like, the product isn't as stable, right? If you had an oxygen attack, you would have, it would be it would be an acetal. And an acetal, right? Because you'd have oxygen carbon, and then that carbon bound to another oxygen. And so that's less stable, because what can happen is it can then go in reverse, right? So probably in solution, you might have that. You might have the oxygen attacking the carbonyl carbon, but then when you produce the acetal, we have a strong tendency to go back, right? We can go back towards the enolate. Whereas if you're producing a carbon-carbon bond, thermodynamically speaking, that's much more stable. So it's thermodynamics, I think, that drives it that way. I would go with that. Okay. All right. Okay. So and then somebody asked about Michael addition. So let's just quickly do that too. Okay, so let's use the same one here. And then let's use this guy. And let's give that a benzene ring too. Why not? So notice now we have two carbonyl containing compounds. One of them already has an alpha beta degree of unsaturation on it. So again, we can enolize, and we're not going to enolize over here because yet again, we don't have a situation. So on one side, there is no alpha proton. Over here, there is an alpha proton, but it's not enolizable because if you were to grab this one and try to put a pi bond there, you would end up with accumulated diene. You'd have a carbon-carbon double bond adjacent to a carbon-carbon double bond, and that's not really a good situation. So it's much, much more favorable to enolize over here at the propanol. So let's go here, let's go here, let's go here. And so here is our enolate. And now this is where it's different. This is where Michael addition is different from aldol condensation because it is a 1,4 addition. And so what that means is now, without going and drawing the resonance structure, just imagine there's a resonance structure where this is like that, right? And that would leave a formal positive charge on this terminal carbon. And so think about the electron deficiency of this terminal carbon. That electron deficiency makes it a very electrophilic site, also because of sterics, right? It's more accessible because it's the edge of the molecule. So electronics plus sterics makes this the best spot for the enolate to attack. And so we get this. So the enolate reforms, and that goes there, that goes there. Okay, so here is the bond that we formed in the Michael addition. So once again, we had a 3-carbon aldehyde. 1, 2, 3. 1, 2, 3. It is the alpha carbon that attacks. So the third carbon better still be there. And then over here, it attacked this edge carbon, which pushed the pi bond here, which pushed the pi bond in the carbonyl up there. Okay, so there's the new pi bond. Now let's go ahead and protonate. Let's get water in there. Stop it. Yeah, I was going to get that. And I'm going to draw this like this so that you can see what I'm going to do next. And then the last thing here is called, I'll write it. Let's go like this. Tautomerization. So the last step in the Michael addition is tautomerization, and a tautomerization is a kind of enolization where we are converting between what are called the enol and keto forms. So this is the enol form because it's an enol because it's an enol, right? We have a hydroxyl on a carbon that is also participating in a double bond, in a carbon-carbon double bond. So it's an alkene, alcohol, enol. And we're going to convert, it's going to isomerize to the keto form because of thermodynamics. And what that means is that this pi bond will get that, and then this will form the carbonyl. And this happens, it's concerted, it's totally concerted. And so we'll end up with this. We end up with the dione. And so a couple things here. We have, it's a 1, 2, 3, 4, a 1,4 addition. And so 1,4 addition, meaning that the, carbon 1 is the carbon that did the attacking, and the new oxygen containing functional group is on carbon 4, 1, 2, 3, 4. And so alpha, beta, gamma, delta, we have, it is on the delta carbon. So it's a dione. We're going to have, we have to have 2 carbonyls, and they have to have precisely this spatial relationship. Okay, so they can't be, this other ketone can't be on carbon 2, can't be on carbon 3. It's got to be on carbon 4. And the reason for this very precise spatial relationship is because of this alpha beta degree of unsaturation, right? There's an alpha, sorry, that's not the right, alpha here, beta here. This alpha beta degree of unsaturation relative to the original carbonyl, that is what makes this terminal carbon, the beta carbon, the electrophilic site, the site that the enolate is going to attack, right? That is the most electron deficient site. It's more readily accessible than the carbonyl carbon even, right? It's going to be more better to attack there. So the enolate attacks at the beta carbon, and that is where this regiochemistry is locked in, right? That's where we end up with this new carbon-carbon bond, and then we protonate to get the enol, and then tautomerization to get the keto form. And so that's really just about bond enthalpies. So what we're saying is that the covalent bonds between polar covalent bonds are more energetically favorable than nonpolar covalent bonds. So more CO bonds brings it to a lower energy. There's a premium on getting a carbonyl over a CC pi bond. So here we have a CC sigma bond and a CC pi bond, but it'll be better thermodynamically if we have a CO sigma bond and a CO pi bond. That ends up bringing the system to a lower energy. So this is thermodynamically driven. Almost always the keto tautomer is favored. There are exceptions. There are situations where, like say, if the enol tautomer is aromatic, then the keto tautomer would break aromaticity. So that's not better. So in such a rare exception, the enol tautomer actually is more energetically favorable and will dominate. But this is not that case. So it will tautomerize to the keto form. This is your standard Michael addition product. It is a 1,4 addition, and it is a dione. It is a dione. So we have 2. Well, actually, no, this isn't a dione because this is an aldehyde on this side. So it's but it's 2 carbonyls, right? So this could be an aldehyde or a ketone. This could actually also be an aldehyde or ketone, but we have 2 carbonyls in with this spatial relationship, and that's your Michael addition. So aldol condensation, you have you get back that first carbonyl, and then you have an alpha beta degree of unsaturation. In the Michael addition, there is no unsaturation because that pi bond becomes the CH sigma bond, and we get the keto tautomer. So you have the dicarbonyl. You have a dicarbonyl compound as the Michael addition product. Okay. Okay, let's see what I missed. Where am I? Where am I? Tommy asks, what is the percent yield of this reaction? This is totally hypothetical, right? You'd have to measure your product at the end, right? You'd have to know the mass the mass of your starting material and the mass of the product that you collect. Leaving group question. Yeah, I did cover that a little bit earlier. Okay. Jay asks if this is AP level chemistry. No, this is organic chemistry 1, so typically sophomore year undergraduate chemistry. Okay, cool. All right, so let's erase this. Hopefully that was helpful. I am absolutely happy to cover any reactions or mechanisms that you guys want, even if they're not on the material that I prepared. So I hope that was helpful. Now let's do the one that I have here, the one that I was planning on doing. Let's erase all this. Okay, so going back a little bit here, let's go back to substitution and elimination, as well as cyclohexane chairs. So we want to draw the product of the following transformation. Now, what are we thinking here? We've got we've got ethoxide, which is strong. So if it's strong, we're thinking E2 or SN2, right? Now, can we do substitution? We're probably not going to get a lot of substitution here because the ethyl group is providing a little bit of steric hindrance, and then we have a secondary substrate, but there is beta branching on both sides. So sterically, there might be trace SN2, but I don't think we're going to be getting very much SN2. So we're going to do E2. Okay, this is going to be an E2 reaction. Now, the thing is, when you're doing E2 on a cyclohexane derivative, you must draw the chair. You have to draw the chair so that you can see which protons are available for beta elimination. So let's draw this out here. Now, I'm going to take this edgemost carbon here as being the one with the bromine, and the bromine is up. So there's my leaving group, and I'm doing that. Now you could draw both chairs. I'm just going to draw the relevant chair, and the relevant chair is the one that has the leaving group in the axial position, right? The leaving group must be axial, and so must be the proton being eliminated. So let me finish drawing this chair. So if we go clockwise, we have a methyl down. So 1 carbon clockwise, we have a methyl down. And then counterclockwise, we have an ethyl up. So here is our ethyl up. I'll just do that. Now, where are the beta protons? So we have a beta proton here, and we have a beta proton here. Now, as I was saying, in order for beta elimination to proceed, we must have the proton being extracted and the leaving group. They must be anti-paraplanar. They must be anti-paraplanar because what is happening is we're forming a pi bond, and pi bonds occur when you have lateral overlap of unhybridized p orbitals. So if we're going from sp3 hybrid atomic orbitals to sp2 hybrid atomic orbitals, we're liberating some p orbitals, and then those have to be parallel. They have to align and overlap. So they can't, right? A pi bond can't happen if the lobes of the p orbitals are not parallel, right? If they're pointed like this, they can't overlap. They have to be like this. And so the only way that's going to work is if they are anti-paraplanar. And in order for two groups on a cyclohexane ring to be anti-paraplanar, they have to be axial, right? And so I won't draw the Newman projection, but if you were to look down that bond, the bromine and the proton would be anti, right? The bromine would be here, and the proton would be here. 180-degree bond angle. They're anti with respect to each other. They have to be anti because the electron density that is going to form the pi bond, those p orbitals need to be parallel, right? So that's the only configuration that works. And so the reason that we had to draw the chair was to realize that this proton is not going to work. That proton is not available for beta elimination because it is not axial and it is not anti to the leaving group. So we are not going to get the proton here. We're not going to get this proton. There's only one proton available for beta elimination, and it's going to be this one. So let's go ahead and get that proton. And then these electrons will form the pi bond and then kick off the leaving group. And then now going back to our top-down view, we have the pi bond here. We have the ethyl group is now planar. And then nothing happened to that methyl group. No chemistry was done there. It is still an sp3 carbon. The methyl is still on the dash bond, and that is going to be our product. So what did we do? So now, if we were over here and we were just looking top down, we would think, all right, I have 2 protons available for beta elimination, and we might even lean towards getting this one because it's a little bit more available sterically. It's on a carbon with a methyl rather than an ethyl. So we might have gone that way, but that would have been wrong. We will get none of that product. So this is not even about a distribution. This is not about Regis selectivity, one more than the other. We will get none of the product with this proton being extracted. It's not going to go because there's no way to get that proton anti-paraplanar to the leaving group. So we cannot form the pi bond there. It won't go. So we had to draw the chair, and again, if you drew both, I encourage you to draw both chairs. But if you can just draw one, that's fine. I just drew one because I knew I was going to put the bromine up and axial because I know that I need my leaving group axial. And then once I have the bromine, I know where the other groups are going to go, right? The methyl was down and the ethyl was up. And so that showed me that I had just one beta proton available. And so we extracted that one, put in the pi bond, kicked off the bromine, and that's that. So this is sp2. This is an sp2 carbon, so that ethyl is planar in the plane of the screen. This one's sp2, right? This one is sp3, so we do have to still show the tetrahedral geometry there. No chemistry occurred there. The methyl was on a dash bond. It remains on a dash bond. No chemistry happened there. So that's a little bit E2 on cyclic systems, right? E2 on cyclohexane derivatives. There's just a little bit more work to do because you have to check the chair to see what is going on, which protons are available, that sort of thing. Okay, let's see what I missed. So Giacomo asks, why does it have to be axial? So a proton that is equatorial is anti to the rest of the ring. So the reason that the cyclohexane chair is so stable, right, or why the equatorial position is stable, right? We're looking, if you could draw a Newman projection for any carbon-carbon bond. And so the point here is that you need the leaving group to be anti to the proton being extracted so that the p orbitals can overlap to form the pi bond. And the equatorial position can never be anti to any other substituent because it's anti to the ring itself. Right, so we're not going to be able to form a pi bond from that position because it's not going to be able to do that. Yeah, or actually, sorry, would be this. Yeah, it's anti to the rest of the ring. Gamma Light, this is Organic Chemistry 1, sophomore year undergrad. Sanjay, yes, it's beta hydrogen. It is so it's so if this is the group in question, then we're saying this this is alpha and then this is beta. So this is alpha to the bromine, this carbon is beta to the bromine, and the hydrogen is on the beta carbon. So it is beta proton. Okay, let's move on. A little bit of nomenclature, why not, right? So we have an alkene, and there are no other substituents other than alkyl. And so we're going to number the carbon chain so as to give the double bond occurring soonest. So should we, first of all, we have the longest carbon chain. That's very easy because we just have one methyl group there. There's nothing to really think about there. Now, are we going to number this carbon chain left to right or right to left? Well, we want the carbon the double bond occurring soonest. So we're going to go 1, 2, 3, 4, 5, 6, 7. So we have a heptene, and then all that's left is we have to name any substituents, and here we only have one. So this is going to be 3-methyl, right? First, we list the substituents, and then we need to say where the double bond is occurring. Otherwise, it would be ambiguous, right? We need to state where the double bond begins. So this is 3-heptene. Also acceptable is 3-methyl hept 3-ene. I like to do it the original way. I think more and more classes are going this way these days, but I don't know. I just like 3-heptene, right? We know that I like to keep heptene together, but anyway, they're identical. They're both acceptable. So we identified the longest carbon chain, numbered it right to left to give the double bond occurring soonest. It begins on carbon 3 as opposed to 1, 2, 3, 4, starting on 4 if we numbered from the other way. We found that there was a methyl on carbon 3. List the substituent first, 3-methyl, and then 3-heptene or hept 3-ene. Yeah, Vishal says it can only happen on the ethyl carbon because of the paraplanar hydrogen. Yes. So this is the only proton that was available for elimination because it's the only one that's axial when the bromine is axial. Right? When the bromine is axial, this proton is axial. This one's equatorial, so not available. So that's why. Okay. Mackenzie, no, it could not be 2-ethyl 2-hexene because we need the longest carbon chain, right? We will always look for the longest carbon chain. The longest carbon chain possible will be the parent chain. And so if we have a 7-carbon chain possible, the 6-carbon chain will not be the parent chain. Okay. Okay, let's do probably one more. Yeah, let's do one more. Oh, E or Z. Thank you. Yeah, Giacomo says, are we going to add E or Z? Yeah, why not, right? So how do we do that? We have, if we want to do absolute configuration, here are the 2 bonds participating in the pi bond, and now there are 2 groups connected to each carbon participating in the double bond. We need to assign the higher priority, which one of them is higher priority over the other. And so over here, that will be this over the hydrogen. And then over here, that will be this over the methyl. And so that's done by Kahn-Ingold pre-log convention, just like when we're assigning R and S. And so the carbon beats hydrogen. So that wins already. So again, we're not looking at a whole group. We're just looking at one atom at a time. So carbon versus hydrogen by atomic number, carbon wins. So that goes. Then over here, carbon and carbon tie. So we have to see what carbon each carbon is attached to. This carbon is attached to hydrogen, hydrogen, hydrogen. This carbon is attached to hydrogen, hydrogen, carbon. Carbon beats hydrogen, so this direction wins. Now, then you think of a line going through the pi bond, and then if the two higher priority groups are on opposite sides, then it's E. So here, right, this is the higher priority group, this is the higher priority group. They're on opposite sides of the plane containing the double bond. If they were on the same side, it would be Z, and you would remember that because Z same side. So this one's E, but if, let's say, the methyl was here and the ethyl was going up that way, it would be Z, and we would just put a Z there. Yes, thank you for reminding me. EZ, absolute configuration. If you are naming an alkene, you're going to want to put that in there. Okay. All right, one more. Let's do this. What reagents will achieve the following transformation? So this is something that a lot of students panic on, right? And so what do we want to talk about here? We've got a 5-carbon alkyne, and then we have a 1, 2, 3, 4, 5, 6, 7-carbon alkene. Okay, so how did we go? There's no other functionality here. These are hydrocarbons. There's no hydroxyls. There's no halogens. What did we do? How did we do this? Okay, now there's one reaction that we need to keep in mind when we're looking at alkynes. Okay, with alkynes, we have to understand that the terminal proton is just barely acidic enough to be extracted. It's pK around 25, I believe, which is certainly not acidic. But if you have a very strong base, like sodamide, so NaNH2, NH2 minus is a very, very strong base. It's so strong a base, in fact, that its conjugate acid, NH3, ammonia, is a base, right? So it's a very, very strong base. And it is so strong that it will grab this terminal proton, and we're going to leave the carbon ion on that alkynyl carbon. So that gets us to here. Okay, so it doesn't look any different except that the implied hydrogen is not there anymore. There is no implied hydrogen, and we have a negative charge. So that terminal alkynyl carbon has a formal negative charge. It has 3 bonds to this other carbon in the triple bond and a lone pair, right? So 5 electrons, 1 more than typical valence of 4, formal negative charge. Now, this is a great SN2 nucleophile. And if we have a carbon nucleophile, we can add more carbon content. So it's easy to make a carbon-containing electrophile, right? All you need to do is make an SN2 substrate, something that can be attacked by a nucleophile. It's harder to get a carbon nucleophile. And so if we want to add 2 carbons, what should we do? Let's just have this attack ethyl bromide. That's a very easy standard thing here. So let's go boom, boom. And after that, we will have this. The triple bond is still there, but we added 2 carbons, right? Plus bromide. So now we have a 1, 2, 3, 4, 5, 6, 7 carbon alkyne, and we want to go to the 7 carbon alkene. But is the alkene E or Z? It's an E, right? So we know that we can reduce alkynes to alkenes, but there are different sets of reactions, right? If we want to do a hydrogenation of an alkyne, there's a few different things that we can do. We can do hydrogenation over platinum metal, but that's going to go all the way to the alkane. We don't want that. We want the alkene, and we want the E alkene. You can do Lindlar's catalyst, but that goes to the Z, so that's no good. But what if we do sodium and liquid aluminum? That is going to get us to the E. So that you kind of have to have memorized. It is important to have memorized your conditions for reducing an alkyne to either an alkane or an E alkene or a Z alkene. So that's hydrogenation over platinum metal. Hydrogen gas over platinum metal, Lindlar's catalyst, or sodium and liquid ammonia In this case, the third is the one that we wanted because we're going from the alkyne to the E-alkene. So we looked at our terminal alkyne. This only works with a terminal alkyne, not an internal one, because it has to have that proton on there. And then we used a very strong base, extracted that terminal alkynyl proton, got the alkynyl nucleophile, the carbon ion there, had that attack just ethyl bromide, simple SN2, so that we could attach that additional 2-carbon fragment on there. And then we did our reduction to get the E-alkene. So that is that one. We will stop there. Let me just make sure there's no other questions. Yeah, that's fine. So yeah, that is it. So for today, we've got just a couple more of these. Once again, I'm working with Chegg to bring you Organic Chemistry 1 office hours every Tuesday at 5 p.m. Pacific time. Next week only, we are going to be live exclusively on the Chegg website. So it will not be live streamed here. If you've been enjoying these study sessions throughout the semester, please join us next week on the Chegg website. It will be exclusively there, and you do have to log into the website to view it. So that will be next week. After that, there will be a few more over here on my channel live streamed, just as all the rest have been. But otherwise, I will see you on the Chegg website next week, 5